Alright, our project was on SM testing. This is our project for 545. I'm Rojit Biyani.
I'm Jovan Trujilo.
And my name is Joseph Gonzales.
Alright, we're going to start with a little outline here. First, we're going to talk about the problem description and get into some input modeling. Then we'll get into some of the assumptions we made from the problem description. And then we'll talk about our arena model that we developed. And then get into the results from the simulation of that model. And then we'll get into some conclusions and recommendations, and then the costs that are estimated for our ideal system that we created. And then we'll do a summary of the whole presentation. Okay, let's get into our problem description. So this problem is for a medical lab testing facility. And in this scenario, we have 5 different test cells and a load and unload area. The samples take about 5 minutes for the load area. And so each of these 9 different part types come in with their various sequences, and they move through the system in a counterclockwise fashion. And it's basically a conveyor belt system, and there's 3 units for each of the cells for a capacity, and there's 1 in the test for each of the cells. Okay, so a little more about the load-unload area. It has a 5-unit buffer plus the 1 unit that's in progress. It also has unlimited space in the exit queue. When an entity gets there, there's 4 possible actions. The first one is the sample holder is empty, and the new sample queue is also empty. So what we would do in that scenario is send the sample holder back to the loop. Another scenario is when the sample holder is empty and the new sample is available. In that case, we load the sample onto the holder and send it to the loop. Another case is sample holder contains the completed sample and the new sample queue is empty, so we'd unload the sample and send the holder back into the loop. And the final case is where the sample holder contains that completed sample that we've just finished and that new sample is available. So we would unload the completed sample and load the new sample into the conveyor belt loop. The 3 main objectives that we gathered from reading the problem description was they wanted scalability, they wanted something that was cost effective, and they wanted each of the parts to get through the system in less than 1 hour. When we were given the data for the case, we looked at the input data which was given to us for a 24-hour time frame from one of their pilot runs, and each hour there was a number of entities that arrived. And so what we did is we took that data and we did distribution on it, and using Arena we did some input analysis, and the 2 closest distributions were an exponential and a beta distribution. And in the end the beta distribution won out because it had the best chi-score test value. And so that's what we use for our arriving entities.
So now we'll talk a little bit about assumptions that we use in the Arena model. Cycle time for testers will use a constant distribution depending on which cell they were on. There will not be any cleaning of the cells or any failure on the tools. There will not be any rush deliveries for any of the samples, and we also the assumption is a 24-hour period per run, and we follow a arrival rate of beta distribution as explained before. This is a high-level overview of the model. As you can see, it's very complex. It describes all the 5 different test cells and the loading and unloading of the conveyor belt as well. So to explain the model, I divided it in 3 pieces. The first one is the arrival to the conveyor. As you can see, the part arrival shows the beta distribution. We did it on a schedule base. The assigned attributes will assign the different attributes. It will give the part as per the distribution given in the problem. Will give a different index to each individual part as well. That will tie to the sequence, the different pictures, and the entity types. Then we'll get to the loading portion of it, in which it will access the conveyor, and the loading on the process will use the loader and finally load it in, start the sequence and load it into the conveyor if a space is available. The second piece is once you're actually in the conveyor belt, now you have to, depending on your sequence, you will have to go to the different cell. as per your sequence. Uh, One of the limitations of the problem was that each cell will have a buffer of three units. So the first piece, this spacing cell, is a decide block that will choose if it will check the queue on the processing cell, and if it is not, if you got more than three, as is explained here, um, it will go back to the conveyor belt following this. If you have the space, you will go through the processing cell, you will be tested, and then you will move to the exit load, and then you will access the conveyor belt. If a space is available, then you will move into the conveyor belt. The last piece is once you exit the systems. Once you completed all the steps in your sequence, then you will be presented to the option of going to the unloading portion of it, in which if the unloader is available, it will pick it up and take it to a different station, and then after that the sampler holder will be removed, and it will go back into the queue. At the end of it, we measure the cycle time, and then finally we dispose of that. So this is a high level picture of our animation. As you can see in the top left corner, you see a tester being in the idle mode. The other ones will show a tester testing a sample, and the arm robot represents the loader and unloader. The squares represent the conveyor belt, and as you can see, the different dots, the different colors represent each part type, depending on what sequence they were assigned.
Okay, so now we're going to talk about the results. To optimize the system based on capacity and cost, we did a factorial design. For each of the 5 cells we picked 2 different levels, either 2 testers per cell or 3 testers per cell. And as you can see in the first table, the average wait times ranged everywhere from 18.46 minutes throughout the entire testing system, all the way up to 210 minutes. And you can see from the green highlighted cells that the best combination was a combination of 2, 3, and 3 testing units for each of the cells. It also minimized the cost of the system. Based on the slopes from the factorial design, we decided to improve the cost by lowering cell 1, which based on the factors of each of the cells, cell 1 was actually the least significant factor in the model. So we could actually lower the number of units in cell 1 to minimize the cost and still be within our time limits of 1 hour. So we also ran 15 replications of this 1, 2, 2, 3, 3 capacity combination, and we found that most of the time we were actually within the 1 hour limits. There were 2 outliers in the model, which, if costs permit, the company could actually go back to using 2 testers on cell number 1 to further minimize tester delay times. To go into more detail about our optimized system compared to just having 1 unit tester per cell, the total entities processed, both system optimizations had roughly about the same number of units coming in, around over 3,000 units coming in, but we show that the optimized system actually had more samples coming out and not being delayed into a long queue. We also see that the half width coming in was reduced due to our improved model of the input modeling using a beta distribution as opposed to a scheduling distribution. The test cell utilization was also improved by varying the unit cell capacities. And finally, the test cell wait time was roughly equivalent for some of the cells, but then also improved for cell number 5, which is actually the most critical cell, holding back the rest of the cells in the system. So based on this analysis, we conclude that the best setup for this test system is to have one tester for unit cell number 1, 2 testers for unit cell number 2, 2 testers for unit cell number 3, 3 testers for unit cell number 4, and 3 testers for unit cell number 5. The only way to actually meet our 1-hour criteria limits is to have 2 load-unload units and 48 sample holders. We also had some ideas to further improve the system by changing the conveyor speed or length, but found that did not actually add any improvement in our throughput or sample times. It turns out that queue lengths increase with longer conveyor length, and decreasing length means lower conveyor capacity, which is not advised. Keeping the conveyor rotation in counterclockwise rotation, because reversing the direction did not have any effect. So with this optimized system, we estimate that the total capital cost is going to be $133,376. Additionally, a fixed cost of $85,000 is acquired for the additional loader-unloader. So in summary, we covered that our problem statement was a medical lab testing company optimizing an automated test system for hospitals. The test system was kept fixed at 5 test cells, but was able to vary the number of actual test units per cell and the number of load-unload areas for further optimization of the system. We used ARENA to simulate and variability analysis to actually optimize the number of testing units per cell to maintain the throughput time per unit sample, as well as optimize the cost of the total system. So our objectives were met, and a cost-effective system was chosen based on this analysis, which shows that we can effectively simulate for scalability, cost-effectiveness, and maintaining sample time throughput.